Yes, good morning one and all. My name is Ramesh Kumar Reddy, working as Assistant Professor in B.V. Rao Institute of Technology, Department of ECE. Today I am going to explain about rectifier topic. So it is one of the topic present in electronic device and circuit subject for first year students. Now coming to rectifiers, here a rectifier is nothing but it is an electrical device that converts alternating current, that is AC, to pulsating DC. So why we need to convert AC to pulsating DC means some applications, if you require DC voltage, so at that time, so we need to convert it into from AC signal to pulsating DC signal. So that's why we preferred rectifiers under such applications. Now this whole process is known as a rectification, and it is also called as converters. Why it is also called as converters means, so it converts AC to pulsating DC. So that's why, so hence it is also called as rectifiers, is also called as converters. Okay, right. Now coming to this one, so this is your alternative current, that is AC signal. So this will be applied to the input to this rectifier. So here input signal is there. So now if you we need to take output here. So this is nothing but output signal. So this is our output signal. So this is our AC signal, this is our output signal, that is nothing but DC signal. So it is not perfect DC. So it is having some AC ripples are also there. So this type of waveform is nothing but it is full wave rectifier output. Why? Because for full wave rectifier it converts AC to pulsating DC under both cycles, that is positive half cycle and negative half cycle, negative and positive cycles. Right. Now coming to types of rectifiers. So here we have different types of rectifiers are there. So that means, so rectifier, so these are all nothing but diode based rectifiers. Why? Because we are using diode for conversion from AC to pulsating DC. We are using diode, so hence it is nothing but diode based rectifiers. So under diode based rectifiers, rectifiers can be classified into basically, that is half wave rectifier and full wave rectifier. So this one and this one. So again full wave rectifier is classified into bridge type rectifier and center tap transformer type rectifier. So these two are comes under full wave rectifier. Now we'll start about one by one. That is, first we'll discuss about half wave rectifier operation. Okay, later we'll see regarding full wave rectifier operation. Yes, now coming to half wave rectifier. So what is half wave rectifier? So see, in the name itself as half wave, so that means it will convert AC voltage to DC voltage, right? So under only half of the waveform, but it doesn't convert AC to pulsating DC during both cycles. So hence it is named itself as a half wave rectifier. So for this we need to construct for half wave rectifier. Here we have to require one diode. So diode is required, right? And as well as one load resistance is also required, that is resistance, load resistance. See, this diode only conducts when the anode is positive with respect to cathode, then current will flows only during the positive half cycle of the input voltage. So for example, if you take this is your diode, so if you want to apply here input signal here, so during positive half cycle only the diode is conduct. So this is anode and this is cathode. So here we are getting output. So during positive half cycle the diode is on, that means forward bias, that is totally it will be short circuit. Now current flows in the circuit, then V0 is equals to Vi. So during positive half cycle only diode is conduct. During negative half cycle diode doesn't conduct. Why? Because during negative half cycle during negative half cycle diode is off, that is reverse bias, that means open circuit. So hence current doesn't flows in the circuit. So why? Because so it is open circuit. So open circuit means so like this. So this is open circuit, hence current doesn't flows in the circuit. So that's why here V0 is equals to 0 for negative half cycle. Okay. Now see this circuit diagram of half wave rectifier. So here we are having AC supply, that is 230 volts, 50 hertz. So that will be given to here step down transformer, and we are having diode and load resistor RL, and this is nothing but our V0 as our output. So this is our Vin. Let us start with operation of the half wave rectifier. If you apply, that is AC signal here, right? So what happens to the step down transformer means this step down transformer downs this 230 volts AC to 12 volts AC or 9 volts AC. So here we are getting output as 12 volts, that is AC only. Again this 12 volts AC voltage is given to this diode. So that means, right? So here during positive half cycle what happened? So here during positive half cycle, right? So during positive half cycle, so anode is positive, so here cathode is negative. Hence here PN junction is forward bias. So forward bias means diode D is on, hence current flows in the circuit. Hence V0 is equals to VI. So you can assume, let us assume, you can assume VI is nothing but Vm sin omega t. So this is our input signal, right? So during forward bias, so diode is on, that means current flows in the circuit, hence V0 is equals to Vi, right? So during negative half cycle what happened? So for negative half cycle, see, so if you apply here, so if you apply here negative half cycle, that means anode is connected to, that is minus and plus. So anode is connected to negative and cathode is connected to positive, hence here PN junction diode is a reverse bias, diode D is off, that means current doesn't flows in the circuit, hence V0 is 0. So this is case 1 and this is case 2, right? So see, so if you apply both cycles, but we'll get only positive half cycle only. Why? Because here during positive half cycle only diode D is on, so hence here V0 is equals to Vin. So during negative half cycle what happens means, so during negative half cycle here V0 is equals to 0. So that is diode D is off. So like that we'll get output waveform. Yes, this is also simplified circuit. So directly you can use as the AC voltage. So here if you apply here positive cycle, that is plus and minus, so diode D is on, so hence it is short circuit. Now current flows in the circuit, hence V0 is equals to Vin. This is under positive cycle. So if you want to go with negative half cycle, so during negative half cycle, so diode D is off, that means it is reverse bias, that means it is open circuit. Hence current doesn't flows in the circuit, hence V0 is equals to 0. So see what I have explained this AC voltage is applied to primary winding of the step down transformer. This step down transformer mainly used to step down the low voltage at the secondary winding, right? So which will be applied to the diode. See, this is our input signal, and here only, so diode is conducts only during positive half cycle. During negative half cycle, diode doesn't conduct, so here output is 0. So again during positive cycle, again diode D is conduct, then V0 is equals to V in. So here also V0 is equals to V in. So here V0 is equals to 0. So in this way you can get the output waveform for this input sinusoidal signal. Yeah, this is during positive cycle, the diode D will be forward bias. So if you want to write down the circuit, circuit diagram, read down this circuit diagram. So it is short circuit means, so it is short circuit. So this is AC supply, that is only positive half cycle. So this is load resistance RL. So here V0. So here D is forward bias means, so that is short circuit, hence current flows in the circuit I. Now V0 is equals to V in. In the same way, for during negative half cycle, diode will be reverse biased. The flow of current will be blocked. So see, this is the modification of the circuit. So this is during negative supply, negative half cycle. Here open circuit. Here current doesn't flows in the circuits. So here V0 is equals to 0. So due to this open circuit, so here V0 is equals to, yes, these are the input and output waveforms. If you apply this sinusoidal signal, it is continuous signal, AC signal, right? So this is our input signal, and this is our output signal. So if you observe input and output waveforms, see, during positive half cycle only, diode D is conduct, and hence V0 is equals to V in. So during negative half cycle, so diode doesn't conduct, that means reverse bias, then current doesn't flows in the circuit, so that means V0 is equals to 0. So again, if you apply the positive half cycle, again here diode D conducts, again output is equals to V in. So again during negative half cycle, so diode doesn't conduct, that means current doesn't flows in the circuit, hence V0 is equals to 0. So like that, for positive half cycle only diode is conduct, during negative half cycle diode doesn't conduct. So this is our output signals. Yes, now this is very important analysis of half-wave rectifier. So why we are going for analysis means, if you want to find out the efficiency, right? So we need to calculate the DC voltage, that means VDC. So this is VAC, and ripple factor denoted by gamma, and efficiency. So this is peak inverse voltage denoted by PIV, and form factor and peak factor, and last one transformer utilization factor. Let us start with analysis of half-wave rectifier by one. First start with DC voltage. Yes, now this is our DC voltage. So what is VDC voltage? So here VDC voltage is equals to nothing but area under the waveform for full cycle divided by complete cycle time period. So this will be, you can rewrite as VDC is equals to C. So integration of 0 to 2 pi. So this is our total time period, that is 2 pi. Why? Because, so if you take input, so this is pi and this is 2 pi. So output is, so here 0. So this is your V0 and this is your V in. So 0 to 2 pi. So here area under the waveform for complete cycle means here, so that means V naught into d of omega t divided by 2 pi. So this is area under the waveform for complete cycle means V naught into d omega t. So here complete cycle time period means 2 pi. So if you common this one, that is 1 by 2 pi. So integration of 0 to 2 pi. So V naught into d of omega t. So what is V naught? So V naught is our output voltage. So output voltage equals to input voltage during first half cycle. That means 0 to pi. Again pi to 2 pi. So what is output voltage? That is 0. So hence you can split it as a, so 1 by 2 pi integration 0 to pi. So what is V naught into d of omega t plus pi of 2 pi. So here again V naught into d of omega t, right. So during 0 to pi interval, so here output voltage is nothing but 0 to pi. So what is output? So V naught is equals to what? Let us assume that, so here V in equals to what? Vm sin omega t, right. So for interval 0 to pi, so what is V naught? So V naught equals to V in. So hence V naught is equals to Vm sin omega t. So that's why here in the place of V naught we have to substitute Vm into sin omega t d of omega t plus, so during pi to 2 pi interval, what is output voltage? Here pi to 2 pi interval, what is output voltage here? This one is 0. So that's why here 0 into d of omega t, right. So this is totally 0. Now coming to here, so 1 by 2 pi integration of 0 to pi Vm into sin omega t into d of omega t. So if you common this Vm here, so Vm by 2 pi integration of 0 to pi sin omega t into d of omega t. So here Vm by 2 pi. So if you integrate sin omega t, what is the value? That is minus cos omega t at the interval 0 to pi. Okay. Now after simplification this one, what we have get means, so here VDC is equals to what? So Vm by pi. So here Vm by pi. Yes. After simplification of this equation, so that is Vm by 2 pi, that is VDC is equals to minus cos pi minus of minus cos 0. So that equals to Vm by 2 pi so here 1 plus 1 that equals to Vm by 2 pi into 2. So 2 cancel. So finally what we'll get? So average DC average voltage or DC voltage VDC equals to Vm by pi. Okay. So this is, in this way you can calculate the DC voltage of half wave rectifier. Now we'll move on to AC voltage or RMS voltage. So to find out AC voltage, so here VAC or VRMS is equals to, so what is the basic formula means? That is square root of area of square waveform under full cycle divided by total time period. So like that, so VAC is equals to square root of here 1 by 2 pi integral 0 to 2 pi, so V naught square d of omega t. right? So again, if you simplify this one, square root of 1 by 2 pi. So here what is V0? So V0 is nothing but our output voltage. So again we need to split it this intervals. So again first take it is 0 to pi, V0 square into V0 square into d of omega t plus integral pi to 2 pi. So V0 square into d of omega t. So again if you simplify this one, so we'll get 1 by 2 pi. So here 0 to pi, what is V0? So under 0 to pi means, so V0 is equals to input voltage, that is V0 is equals to what? VI. If VI is equals to Vm sin omega t, so during positive cycle, that means interval 0 to pi, so diode D is on, hence current flows in the circuit. So V0 is equals to VI, that equals to Vm sin omega t. So during interval 0 to pi, so what is output voltage? Here Vm square into sin square omega t d of omega t plus integral pi to 2 pi. So what is V0? So pi to 2 pi means that is negative off cycle. So diode is off, hence V0 is equals to 0. So here 0 into d of omega t. So this one is completely 0. Okay. Now after simplification this equation, see here 1 by 2 pi integral 0 to pi, here Vm square into sin square omega t d of omega t. Now if you common this one here, that is 1 by 2 pi into Vm square, that is integration of pi into sin square omega t d of omega t. Now what is sin square omega t? So sin square omega t is formula is, so we have sin square omega t is equals to 1 minus cos 2 omega t by 2. Okay. So again substitute in the place of sin square omega t. If you substitute this value, then here square root of Vm square by 2 pi integral of 0 to pi, that is 1 minus cos 2 omega t by 2 into d of omega t. Okay, right. Here if you common this one, that means 2. So what will get here? So VAC is equals to what? Square root of Vm square by 4 pi, right. So here integral of 0 to pi 1 minus cos 2 omega t by 2. Sorry, 2 already common here. So 1 minus cos 2 omega t d of omega t, right. Right. So here VAC is equals to square root of Vm square by 4 pi. So here if you integrate this one, so what will get means, so if you integrate 1 minus cos 2 omega t, here omega t minus sin 2 omega t by 2 under the interval 0 to pi. So after simplifying this one, so we'll get square root of Vm square by 4 pi into, here omega t means that is pi minus 0. So total here value will get pi minus 0. So here pi cancel. So finally So Vm square by 4 pi under root. So that equals to Vm by, sorry, pi is already cancelled here, Vm square by 4. So that equals to Vm by 2. So hence, so finally what we'll get? So VAC is equals to Vm by 2. So in this way you can calculate AC voltage for half-wave rectifier. So now coming to ripple factor. So it is very important one. So what is ripple factor? So here, so ripple factor means RMS value of AC component divided by DC component, that equals to V gamma RMS divided by V DC. So what is V gamma comma RMS? That equals to square root of V RMS square minus V DC square. So ripple factor is denoted by letter gamma. So gamma is equals to what? So square root of V RMS square minus V DC square by V DC. After simplifying this one, so what we'll get? So here gamma is equals to square root of V RMS square by V DC square minus 1. So this is your ripple factor formula. Okay, how to calculate ripple factor for half-wave rectifier, right? So how to calculate ripple factor for half-wave rectifier means, so we have just now we have calculated VDC value and VRMS value. Just substitute these values in this VRMS and VDC square, then you can find ripple factor. So here gamma is equals to, so what is VRMS value? So VRMS value for half-wave rectifier is what? So VRMS equals to Vm by 2 and VDC is equals to Vm by pi. So these are the RMS and DC voltages of half-wave rectifier. If you substitute these values in this equation, then you can find out ripple factor gamma. So gamma is equals to what? Square root of VRMS means Vm square by 4 by Vm square by pi square minus 1. So after simplify this equation, what we'll get? So square root of, so Vm square by 4 into pi square by Vm square. So Vm square cancel. Here minus 1 is there. Okay. So finally what we'll get? So pi square by 4 minus 1. So after simplify this equation, we'll get 1.21. So this is ripple factor for, half-wave rectifier is 1.21. So in this way you can calculate ripple factor. Without knowing the values of VRMS and VDC values, we can't find out the ripple factor. First of all, we need to calculate VRMS and VDC only, then only you can calculate the ripple factor of half-wave rectifier. Now coming to efficiency. So what is efficiency? So efficiency is nothing but DC power, it is the ratio of DC power divided by AC power. So what is DC power? So what is the formula for DC power? So actually DC power formula is VDC square by RL by, and AC power formula is VAC square by RL. So if you cancel RL, then what will get? So eta is equals to VDC square by VAC square. Okay. So what is VDC square value? So just now we have calculated, that is, what is the value? So Vm square by pi square by, so what is VAC value? So Vm square by 2, that means 4. Okay, so that equals to what? So Vm square by pi square into 4 by Vm square. So Vm square cancels. So finally eta is equals to 4 by pi square. So that value is equals to 0.406. 0.46. So if you calculate a percentage of efficiency, then for this value, that is just we need to multiply this value with 100, then we can get 40.6%. So this is our efficiency of half-wave rectifier. So efficiency of half-wave rectifier is what? .6%. So in this way you can calculate the efficiency. Now peak inverse voltage. What is peak inverse voltage? So this is very important, and it is denoted by letter PIV. So it is defined as maximum reverse voltage that the diode can withstand without destroying the junction. Okay. The peak inverse voltage across the diode is peak of the negative half cycle. That means for half-wave rectifier, so what is peak inverse voltage means? So the peak of negative half cycle means that is Vm. So hence peak inverse voltage for half-wave rectifier is Vm only. Now form factor. So form factor. So basically form factor formula is nothing but what? That is RMS value. RMS value means VAC divided by average value. That means DDC. What is VAC value? We know VAC value. So what is VAC value? That is Vm by 2 by what is VDC value? Vm by pi. So what will get? So Vm by 2 into pi by Vm. So Vm cancel. So finally what will get? Pi by 2. If we simplify this one, we'll get 1.57. So here form factor for half-wave rectifier is 1.57. In the same way, you can calculate the peak factor. So what is peak factor? So here peak factor of output voltage, that is peak factor of output voltage is nothing but here Vm only, and RMS value of output voltage means that is VAC. So here Vm by what is VAC value? We know about VAC value, that is Vm by 2. So Vm by 2 by Vm, that equals to what? Vm cancel, finally 2. So peak factor for half-wave rectifier is 2. Next we are going for next parameter or for analysis of half-wave rectifier. So this is your final one, that is transformer utilization factor. First of all, what is transformer utilization factor? And it is denoted by letter TUF. So it is nothing but DC power delivered to load divided by AC rating of the transformer secondary. So here DC power delivered to load means, what is the value here? DC power means, so power ante PDC, that is PDC divided by PAC rated. Rated means why? Because here transformer secondary means AC rating of transformer secondary means, so that's why here PAC rated. Now how to find out PDC value? So we know that PDC value is equals to what? VDC square by RL. That means V square by R. Okay. In the same way, how to calculate PAC rated? So we know PAC rated is nothing but, for transformer secondary, rated secondary voltage is nothing but Vm by root 2, and the RMS value of current flowing through the secondary is Im by 2, not Im by root 2. Okay. So finally, so PAC rated is nothing but Vm by root 2 into Im by 2. Okay. Now, so TUF is equals to what? Just substitute PDC value and PAC value in this equation. then you can get transformer utilization factor. So that is VDC square by RL by Vm by root 2 into, so here Im. So Im, we can write Im formula in terms of I equals to, general formula is I equals to V by R, that is Vm by RL. So here Vm by RL. So here VDC square by RL by Vm square by root 2 into RL. Okay, this RL cancel. So finally what we'll get here? Here root 2 into VDC square by here Vm square. So we know that VDC square, what is VDC value? So VDC value is how much? So VDC value is Vm by pi. So root 2 into Vm square by pi square into Vm square. So actually here 2 is there. Why? Because here 2 is there. So here also 2. Here 2 root 2 into pi square. So finally what we will get? So TUF is equals to 2 root 2 by pi square. If we simplify this one, we can get 0.285. So transformer utilization factor for half-wave rectifier is how much? That is 0.285. So in this way we can calculate all parameters of half-wave rectifier. So this is nothing but analysis of half-wave rectifier. In the next class, we'll discuss about full-wave rectifier operation as well as how to analyze the full-wave rectifier in terms of how to find out average value, RMS value, efficiency, ripple factor, form factor, peak factor, as well as transformer utilization. Last one, that is advantage and disadvantage of half-wave rectifier. That means what are the advantages of half-wave rectifier? It is simple in construction. Why? Because simple in construction means it requires only one step down transformer and diode, one resistor. So that's why it is simple construction, and cost also efficient. So it is very less cost. Now coming to disadvantages, filters are required to get pure DC. Why? Because by using half-wave rectifier, we can't get perfect DC. So AC ripples are there. We need to remove that AC ripples. These filters are required. Now AC power delivers during half cycle only. So here output voltage is low. So here output voltage is low. Why? Because it delivers only half cycle only. And here ripple factor is 1.21. Just now we have calculated. So it is very high compared to full wave rectifier. So if you want to perfect DC, ripple factor value is must and should be less value. That will be achieved by using full wave rectifier. For half wave rectifier, ripple factor value is 1.21 only. Now efficiency, just now we derived this one, efficiency is 40.6% only. That is also very less compared to full wave rectifier. So these are the advantages and disadvantages of half wave rectifier. Thank you.
Vishnu Audio Visual Center, like and share and subscribe and click bell icon.